The universe is a vast, intricate puzzle, and every star, every galaxy, every particle is a piece waiting to reveal its secret. But what if the answers to the cosmos' greatest mysteries aren't found in the endless expanse of space, but in the tiniest building blocks of reality itself? What if the quantum realm, a place so small it defies imagination, holds the key to understanding everything? Today, we embark on a journey unlike any other, 20 quantum quests for cosmic truths. This isn't just a dive into the science of the cosmos, it's a voyage into the very fabric of existence, where quantum physics and cosmic exploration collide in ways that will challenge everything you thought you knew. From the bizarre behavior of particles to the mind-bending nature of reality itself, we'll uncover truths that bridge the gap between the infinitesimal and the infinite. Are you ready to explore how the quantum realm might hold the answers to the universe's deepest questions? Let's begin. Picture two particles, separated by millions of light years, yet somehow bound together in an invisible dance. If one spins clockwise, the other instantly spins counterclockwise, no matter the distance between them. This isn't science fiction, it's quantum entanglement, one of the most baffling and beautiful mysteries of the universe. Albert Einstein famously called it spooky action at a distance, and for good reason. It defies everything classical physics taught us about how the universe should work. In the world of Newton and Einstein, nothing can travel faster than light, and objects are only influenced by their immediate surroundings. But entangled particles seem to laugh at these rules, communicating instantaneously across cosmic distances as if space and time don't exist for them. So, what's really going on here? At its core, entanglement suggests that the universe might be far more interconnected than we ever imagined. Imagine the cosmos as a vast, invisible web where every particle is subtly linked to every other, creating a tapestry of relationships we're only beginning to understand. This isn't just a curious quirk of quantum mechanics. It could hold profound implications for how we think about reality itself. Could entanglement be a clue to the universe's hidden unity? A hint that, at the deepest level, everything is connected in ways we can't yet fully grasp. And then there's the question of communication. If entangled particles can influence each other instantly, could we one day harness this phenomenon for faster-than-light messaging across the stars? While the answer is still uncertain, the possibilities are tantalizing. But entanglement doesn't just challenge our understanding of communication, it also nudges us toward another cosmic puzzle: quantum gravity. If space and time can be bent or even ignored by entangled particles, what does that mean for the fabric of the universe itself? This first quest into the nature of quantum entanglement is just the beginning, a doorway into a deeper exploration of how the cosmos is stitched together. Imagine trying to fit two puzzle pieces together, only to realize they were never designed to match. That's the challenge scientists face when attempting to unify quantum mechanics, the science of the incredibly small, with Einstein's theory of general relativity, which governs the vast cosmos. Quantum mechanics works beautifully to explain the behavior of particles at the tiniest scales, while general relativity describes the curvature of spacetime and the motion of massive objects like stars and galaxies. But when you try to merge these two frameworks, they clash in ways that defy our current understanding of reality. This isn't just an academic exercise, it's a quest to unlock the deepest secrets of the universe. Why does this matter? Because some of the most fascinating cosmic phenomena, like black holes and the Big Bang, exist at the intersection of these two realms. A black hole, for instance, is an object with such immense gravity that it warps spacetime to an extreme degree. Yet it's also incredibly small at its core, a place where quantum effects should dominate. Without a unified theory, we can't fully explain what happens inside a black hole or how the universe began. It's like trying to tell a story with half the pages missing. To tackle this challenge, scientists have proposed groundbreaking ideas like string theory and loop quantum gravity. String theory suggests that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. Picture these strings as threads in a cosmic tapestry, each vibration creating a different particle or force. Loop quantum gravity, on the other hand, proposes that spacetime itself is made up of tiny, interconnected loops, like a fabric woven from countless threads. Both theories aim to bridge the gap between the quantum and cosmic worlds, offering new ways to understand the fabric of reality. But this isn't just about theoretical elegance, it's about testing these ideas in the real world. And black holes, those enigmatic cosmic giants, might hold the key. As we probe deeper into their mysteries, we're not just studying these bizarre objects, we're also testing the limits of our understanding of the universe itself. What happens when you cross the event horizon? What lies at the singularity? These questions push us closer to the unified theory we seek, a theory that could rewrite the story of everything. Black holes are cosmic enigmas, regions of space where gravity is so intense that not even light can escape. But what happens to the information of anything that falls into a black hole? This question lies at the heart of one of the most perplexing mysteries in modern physics, the black hole information paradox. Imagine tossing a book into a fire. The book might burn, but its information, every word, every sentence isn't truly lost. It's transformed into ash and smoke, still traceable in some form. But with black holes, the rules seem to break down. When matter crosses the event horizon, the boundary beyond which nothing can return, it appears to vanish completely, taking its information with it. This challenges a fundamental principle of quantum mechanics. Information cannot be destroyed, so where does it go? Enter Stephen Hawking, who revolutionized our understanding of black holes by proposing that they aren't entirely black. In the 1970s, Hawking discovered that black holes emit radiation, now known as Hawking radiation. This occurs due to quantum effects near the event horizon, where pairs of particles and antiparticles constantly pop in and out of existence. Occasionally, one particle falls into the black hole while the other escapes, carrying energy away. Over time, this process causes black holes to slowly evaporate. But here's the catch. Hawking radiation appears to be random, carrying no information about what fell into the black hole. If the black hole eventually vanishes, what happens to the information it once contained? This is the essence of the paradox. Recent breakthroughs, however, have begun to shed light on this cosmic puzzle. One compelling idea is the holographic principle, which suggests that all the information swallowed by a black hole might not be lost after all. Instead, it could be encoded on the surface of the event horizon, like a cosmic fingerprint. Think of it as a hologram, where a three-dimensional image is stored on a two-dimensional surface. In this case, the event horizon acts as a kind of memory bank, preserving the information of everything that enters the black hole. This concept not only offers a potential solution to the information paradox, but also hints at a deeper connection between gravity and quantum mechanics, two realms of physics that have long resisted unification. The implications of this paradox stretch far beyond black holes themselves. It touches on the very nature of reality, challenging our understanding of space, time, and the fabric of the universe. If information can be preserved on the event horizon, it suggests that the cosmos operates like a vast, interconnected system where nothing is ever truly lost. This quest to decode the black hole information paradox isn't just about solving a scientific mystery, it's about uncovering the hidden quantum signatures that shape the universe itself. And as we continue to explore, we're reminded that the cosmos is far stranger and more wondrous than we ever imagined. If you've ever wondered how the universe went from a hot, dense soup of particles to the vast web of galaxies we see today, the answer lies in the cosmic microwave background, or CMB. This faint glow, the oldest light in the universe, is like a snapshot of the cosmos when it was just 380,000 years old. But hidden within this ancient light are quantum signatures, tiny ripples from the early universe that tell a story far older than anything we can see with our eyes. These ripples, born from quantum fluctuations in the first moments after the Big Bang, acted like cosmic seeds. Over billions of years, those tiny variations in density grew, pulled by gravity, and became the galaxies, clusters, and vast cosmic structures we observe today. Think of it like this: the early universe was a canvas with faint brushstrokes, and those brushstrokes became the galaxies and voids we now see as the universe's grand artwork. To uncover these quantum fingerprints, scientists rely on tools like the Planck satellite, which mapped the CMB with incredible precision. Planck's data revealed the faintest temperature differences in the CMB, less than 100,000th of a degree. But these tiny variations are the breadcrumbs that lead us back to the universe's infancy. They're not just random patterns, they're the echoes of quantum mechanics at work, stretching across space and time, but the story doesn't end there. These quantum signatures might also hold clues to something even more profound: hidden dimensions. Some theories suggest that the patterns in the CMB could reveal the presence of extra dimensions beyond the three we experience every day. Imagine the universe as a multidimensional tapestry, with threads we can't yet see, but whose influence might be written in the CMB's subtle patterns. What if these ancient quantum imprints are the key to unlocking a deeper understanding of reality itself? What if the universe isn't as simple as the three dimensions we see and move through every day? Enter the fifth quest, the search for extra dimensions. It's a mind-bending idea, but one that could hold the key to understanding the deepest mysteries of the cosmos. According to string theory, the universe might not be limited to just length, width, and height. In fact, it suggests there could be as many as 11 dimensions, all intricately woven into the fabric of reality. But if that's true, where are they? Why don't we see them? The answer lies in something called compactification. Imagine a piece of paper. To us, it looks flat and two-dimensional. But if you zoom in close enough, you might notice tiny fibers running through it, structures that hint at a hidden complexity. Now, think of those fibers as extra dimensions, curled up so tightly that they're invisible to the naked eye. This is how physicists propose higher dimensions might exist, folded and compacted at scales so small they're beyond our everyday perception. It's a strange concept, but one that could explain why gravity, for example, seems so weak compared to other forces. Maybe it's leaking into these hidden dimensions, spreading its influence where we can't see. So how do we even begin to search for something we can't directly observe? This is where cutting-edge experiments like the Large Hadron Collider come into play. By smashing particles together at unimaginable speeds, scientists hope to catch a glimpse of these elusive dimensions. If extra dimensions exist, they might leave behind subtle clues, like tiny ripples or disturbances in the data. It's like listening for echoes in a vast, silent chamber, every anomaly could be a whisper from a dimension we've never seen. But the implications go even further. These hidden dimensions might also hold the secrets to dark matter and dark energy, the mysterious forces that make up the vast majority of our universe. If gravity behaves differently in higher dimensions, it could help explain why dark matter seems to influence galaxies the way it does. And if energy is distributed across these extra layers, it might shed light on why the universe is expanding faster than we expected. The search for extra dimensions isn't just about satisfying our curiosity. It's about unlocking the very framework of reality itself. In the vast expanse of the cosmos, there's a shadowy presence that defies our understanding, dark matter. It doesn't emit light, reflect it, or interact with it in any way we can detect. Yet, its gravitational pull shapes galaxies and holds the universe together. But what exactly is dark matter made of? This is where the quantum world steps in, offering a tantalizing clue. Scientists hypothesize that dark matter might be composed of exotic quantum particles, entities so strange and elusive that they challenge everything we know about the fabric of reality. Two leading candidates have emerged in this cosmic detective story: actions and WIMP, or weakly interacting massive particles. Actions are hypothetical particles so light and ghostly that they barely interact with ordinary matter. WIMP, on the other hand, are thought to be heavier but equally shy, avoiding detection as they drift through space. Both could explain the gravitational effects we observe, how galaxies spin faster than they should, or how light bends around massive objects in ways that visible matter alone can't account for. These particles might be the missing pieces of the dark matter puzzle, hiding in plain sight yet just out of reach. To catch these cosmic phantoms, scientists have devised ingenious experiments. Imagine deep underground laboratories, shielded from cosmic rays, where cryogenic detectors wait in near absolute zero temperatures. These detectors are designed to pick up the faintest whispers of interaction, a single particle bumping into an atom, leaving behind the tiniest trace of energy. It's like trying to hear a pin drop in a thunderstorm, but these experiments bring us closer than ever to understanding dark matter's true nature. Picture dark matter as the cosmic shadow cast by the universe's hidden architecture. Just as shadows reveal the shape of an object without showing its details, dark matter's gravitational influence hints at something profound lurking in the void. But this shadow isn't static, it's dynamic, shaping the universe on the grandest scales. And as we peel back the layers of this mystery, we're led to an even deeper enigma: dark energy. This force, which drives the universe's accelerated expansion, may be intertwined with dark matter in ways we're only beginning to grasp. Together, they form the unseen framework of our cosmos, a story still being written in the language of quantum particles and cosmic shadows. What if the very fabric of the universe is being stretched apart by a mysterious force we can't see or touch? This is the enigma of dark energy, a force so powerful it's accelerating the expansion of the cosmos. But where does this energy come from? Some scientists believe the answer might lie in the quantum realm, the strange, unpredictable world of the very small. Picture this: empty space isn't truly empty. Even in a vacuum, particles flicker in and out of existence, a phenomenon known as vacuum energy. This energy, according to quantum theory, could be the source of dark energy. But here's the catch: when physicists calculate how much energy should be present, the numbers don't match what we observe. This discrepancy is one of the biggest mysteries in modern physics. Another idea ties dark energy to Einstein's cosmological constant, a term he introduced to describe a repulsive force balancing gravity. While Einstein initially dismissed it, the cosmological constant has made a comeback as a potential explanation for dark energy. Yet, even this theory struggles to account for the precise amount of energy driving the universe's expansion. Now, let's step back to the early universe. Quantum fluctuations, tiny ripples in the fabric of spacetime, may have played a crucial role in shaping the cosmos we see today. These fluctuations could have set the stage for dark energy's dominance, acting like seeds that grew into the vast cosmic structures we observe. Imagine the universe as a cosmic spring, constantly pushing outward, stretching galaxies farther apart with each passing moment. But this isn't just about our universe. The multiverse hypothesis suggests that dark energy might vary across different universes, each with its own unique properties. Could the value of dark energy in our universe be a random outcome, or is there a deeper reason behind it? This quest not only challenges our understanding of dark energy, but also connects to the broader question of whether our universe is just one of many. As we explore these ideas, we're reminded that the quantum world and the cosmos are deeply intertwined, and the answers we seek might lie in the delicate balance between them. At the very heart of quantum mechanics lies a concept that stretches the boundaries of our imagination: the multiverse. Picture this: every time a quantum event occurs, like the spin of a particle or the decay of an atom, the universe doesn't just choose one outcome. Instead, it splits. Each possible outcome becomes reality, but in a separate, parallel universe. This is the essence of the many worlds interpretation, a bold idea that suggests our universe is just one of countless others, branching endlessly like the sprawling limbs of a cosmic tree. Each branch represents a different path, a different reality, born from the infinite possibilities of quantum mechanics. Now, let's take a step back and think about what this means. If every quantum decision creates a new universe, then there's a version of reality where every conceivable event has happened. A universe where dinosaurs never went extinct, where humanity discovered interstellar travel centuries ago, or even one where you made a different choice this morning. The implications are staggering, not just for science, but for how we understand existence itself. Are we simply one thread in an infinite tapestry of realities? And if so, what does that say about the nature of truth? Could there be universes where the laws of physics are entirely different, or where life as we know it never emerged? This idea of infinite branching universes also brings us to one of the most profound mysteries in cosmology: the fine-tuning of our universe. Why do the constants of nature, like the strength of gravity or the charge of an electron, seem so perfectly calibrated to allow life to exist? Some scientists argue that in a multiverse, every possible combination of physical laws exists somewhere. In most of those universes, life might be impossible. But in a rare few like ours, everything aligns just right. It's as if we've won the cosmic lottery, not by chance, but by necessity. The multiverse theory offers a possible explanation. We exist because we're one of the lucky branches on that cosmic tree, where conditions allowed complexity and life to flourish. But how does quantum mechanics tie into this? At its core, quantum branching is driven by probabilities. Every particle, every atom, exists in a state of uncertainty until it's observed. And when that observation happens, the universe splits, creating new realities where each possible outcome plays out. This process isn't random. It's governed by the laws of quantum mechanics, which dictate the probabilities of each outcome. So, if the multiverse is real, it's not just a chaotic jumble of universes. It's a structured, infinite web of possibilities, each one following the same fundamental rules, even if their outcomes are wildly different. As we ponder the multiverse, it's hard not to feel a sense of awe. The idea that every choice, every event, spawns a new reality challenges our understanding of existence. It raises questions about free will, about destiny, and about the very nature of truth. Are there universes where cosmic truths are entirely different? Or is there some underlying principle that connects them all? These are the kinds of questions that make the multiverse not just a scientific theory, but a gateway to exploring the deepest mysteries of the cosmos. And as we continue our quantum quest, we'll see how this idea might hold the key to understanding why our universe is the way it is, and what it means for the fabric of reality itself. What if the universe itself were a cosmic lottery, and we just happened to hit the jackpot? That's the mind-bending question at the heart of our ninth quantum quest, the fine-tuning of the universe. Think about it. The fundamental constants that govern everything, from gravity to the speed of light, are set with such precision that even the tiniest change would make life as we know it impossible. It's as if the universe was designed with us in mind. This idea is known as the anthropic principle, and it raises one of the most profound mysteries in science. Why do these constants have exactly the values they do? Quantum mechanics offers a fascinating lens to explore this. At the quantum level, particles behave unpredictably, existing in a haze of probabilities until observed. Could this same uncertainty play a role in the universe's fine-tuning? Some scientists suggest that the constants we see might not be fixed at all, but are instead the result of an infinite number of quantum possibilities collapsing into the reality we experience. It's a staggering thought that the very rules of existence might be as fluid as the quantum foam at the smallest scales. But what if our universe isn't the only one? Enter the multiverse theory, a concept that suggests there could be countless other universes, each with its own set of constants. In this vast cosmic landscape, most universes might be barren, unable to support life. Ours, however, just happens to be one of the rare ones where the conditions are perfect. It's like buying a single lottery ticket in a sea of trillions, yet here we are, living in the universe that won. The odds of this fine-tuning are almost beyond comprehension. To put it in perspective, imagine tuning a radio to pick up a specific frequency. Now imagine that frequency is so precise that even the slightest nudge would drown it out in static. That's the kind of precision we're talking about with the universe's constants. It's no wonder some see this as evidence of a deeper order, while others view it as a cosmic fluke. As we ponder these questions, we're led to an even bigger mystery, the nature of time itself. Why does time flow in one direction, and is it possible that time, like the constants of the universe, is another finely tuned element in the grand cosmic equation? These are the kinds of questions that don't just challenge our understanding of the universe, they challenge us to rethink our place within it. Time, as we experience it, flows in one direction forward. But in the quantum realm, this familiar arrow of time begins to blur. Here, particles don't just follow a linear path, they can exist in multiple states at once, a phenomenon known as quantum superposition. Imagine a cosmic hourglass where sand flows not just downward, but in every direction simultaneously. This is the strange and fascinating world of quantum time. At the heart of this mystery lies the idea that time, much like space, might not be as fixed as we once believed. In classical physics, time is a steady, unchanging backdrop against which events unfold. But quantum mechanics suggests something far more dynamic. Particles can be in two places at once, and they can also exist in multiple moments at once. This challenges the very foundation of our understanding of time's flow. One of the most intriguing experiments exploring this idea is the quantum clock. Unlike traditional clocks that tick away in predictable rhythms, quantum clocks operate on the behavior of particles in superposition. These clocks don't just measure time, they reveal its fluidity. In some experiments, particles appear to experience time in ways that defy our classical intuition, suggesting that time itself might be more malleable than we ever imagined. What does this mean for the universe? If time isn't as rigid as we think, it opens the door to questions about causality, the nature of reality, and even the possibility of time loops or parallel timelines. And as we delve deeper into these questions, we begin to see connections to another profound mystery: quantum consciousness. Could the nature of time be tied to the way our minds perceive reality? This quest doesn't just challenge our understanding of time, it invites us to rethink the very fabric of existence. What if consciousness isn't just a product of the brain, but something far more profound, something woven into the very fabric of the universe? This is where our 11th quantum quest takes us, into the speculative yet mesmerizing realm of quantum consciousness. At the heart of this idea lies a bold proposition: that our minds might not be confined to the classical world of neurons and synapses, but could instead be deeply entangled with the quantum universe. Theories like orchestrated objective reduction, or ORCH, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggest that quantum processes within the brain's microtubules could be the seat of consciousness. These tiny structures might act as quantum computers, processing information in ways that classical physics alone can't explain. But how does this connect to the cosmos? Imagine the universe itself as a vast, interconnected mind, with quantum processes acting as threads that bind everything together. Just as particles can be entangled, instantaneously influencing one another across vast distances, so too might consciousness be a phenomenon that transcends individual brains, linking us to the universe's quantum fabric. This idea doesn't just challenge our understanding of the mind, it redefines our place in the cosmos, suggesting that we are not separate observers but active participants in a quantum dance. Metaphors can help us grasp this profound connection. Picture a symphony where each note represents a quantum event, and the brain is the conductor, orchestrating these events into the melody of consciousness. The universe, in this view, is not a cold, indifferent void but a living, thinking entity with consciousness as its fundamental feature. It's a poetic and provocative idea, one that blurs the line between science and philosophy, inviting us to rethink what it means to be aware. And here's where things get even more fascinating. If consciousness is quantum in nature, could it also play a role in the origin of life itself? Some scientists speculate that quantum processes might have been crucial in the emergence of life from inanimate matter, acting as a bridge between the physical and the living. This leads us seamlessly into our next quest, where we'll explore how quantum mechanics might have set the stage for life to emerge in the universe. The connection between quantum consciousness and the origins of life is a tantalizing thread, one that will unravel further as we continue our cosmic journey. What if the spark of life itself was born from the strange and mysterious world of quantum mechanics? This is the question at the heart of our 12th quest, the quantum origins of life. At first glance, life and quantum physics might seem like they belong to entirely different realms, one rooted in biology, the other in the subatomic. But what if the two are deeply intertwined? Scientists are now uncovering evidence that quantum phenomena, like tunneling and coherence, may have played a pivotal role in the emergence of life as we know it. Take enzymes, for example, the molecular machines that drive countless biochemical reactions. These reactions are so precise and efficient that classical physics alone can't fully explain them. Enter quantum tunneling, a phenomenon where particles essentially teleport through barriers they shouldn't be able to cross. It sounds like science fiction, but this quantum trick is what allows enzymes to speed up chemical processes critical to life. Without it, the chemistry of life might grind to a halt. It's as if nature has a secret toolkit, and quantum mechanics is one of its most powerful tools. But the quantum connection to life goes even deeper. Some researchers propose that quantum coherence, a state where particles behave in unison, almost like a perfectly synchronized dance, could have been essential in the early stages of life's evolution. Imagine a delicate balance where quantum effects allowed molecules to feel out the most efficient pathways for forming complex structures, like the first self-replicating molecules. It's like the universe itself was guiding the process, nudging life into existence with a quantum spark. And if quantum mechanics played a role here on Earth, could it also be the key to finding life elsewhere? The same principles that might have sparked life on our planet could be at work in the icy oceans of Europa, the methane lakes of Titan, or even the atmospheres of distant exoplanets. The search for quantum life beyond Earth isn't just about finding water or organic molecules. It's about uncovering the universal quantum signatures that might hint at life's presence, no matter how alien it might seem. So, as we continue our journey through the cosmos, we carry with us not just the tools of biology and chemistry, but the insights of quantum physics, opening new doors to understanding the origins of life itself. Imagine a world where life doesn't just exist in the familiar forms we know on Earth, but thrives in ways that defy our understanding, life that dances to the rhythm of quantum mechanics. Could the cosmos be teeming with organisms that rely on the strange, almost magical behaviors of particles to survive and communicate? This is the heart of our 13th quest, the exploration of quantum life in the universe. Here on Earth, extremophiles organisms that flourish in the harshest environments offer us a glimpse into the resilience of life. From the scorching heat of hydrothermal vents to the crushing pressures of the deep ocean, these remarkable creatures adapt to conditions that seem impossible. But what if their survival isn't just about physical toughness? What if hidden within their biology lies a quantum secret, a mechanism that allows them to harness the peculiar properties of particles like superposition or entanglement? If life on Earth can push boundaries this far, why couldn't alien life evolve to use quantum processes as a cornerstone of existence? Picture a distant exoplanet, bathed in the faint glow of a red dwarf star. Beneath its surface, a network of quantum gardens pulses with energy, a living ecosystem where organisms communicate not through sound or light, but through entangled particles. These beings might not have eyes or ears as we know them. Instead, they could sense their surroundings through quantum vibrations, exchanging information instantaneously across vast distances. Such a system would be far more efficient than anything we've ever seen, allowing life to flourish in environments where traditional methods of communication would fail. The implications are staggering. If alien life has evolved to use quantum phenomena, it could explain why we've yet to detect it. Our current methods of searching for extraterrestrial intelligence rely on electromagnetic signals, radio waves, light, and other forms of energy. But what if these civilizations are communicating through quantum channels, invisible to our instruments? The search for quantum communication in the universe might not just be a scientific endeavor. It could be the key to unlocking one of the greatest mysteries of all: are we alone? As we ponder these possibilities, we're reminded that the universe is far stranger and more wondrous than we often give it credit for. Quantum life, if it exists, would challenge our understanding of biology, physics, and even what it means to be alive. And so, our quest continues, not just to find life beyond Earth, but to discover the cosmic truths that might reshape our place in the universe. Imagine a universe where messages travel faster than light, where information leaps across galaxies in the blink of an eye. This isn't science fiction, it's the tantalizing promise of quantum communication. At the heart of this idea lies quantum entanglement, a phenomenon where two particles become so deeply connected that the state of one instantly influences the other, no matter how far apart they are. It's as if the cosmos itself has woven an invisible thread between them, allowing whispers of information to travel faster than any signal we've ever known. But how could this seemingly magical process revolutionize our ability to communicate across the stars? Picture this: a quantum network spanning the galaxy, where entangled particles serve as the ultimate messengers. Instead of waiting years for a signal to reach a distant star system, we could send and receive information instantaneously. This isn't just about speed. It's about unlocking a whole new way of understanding the universe. Imagine sending a message to a probe near Alpha Centauri and receiving a reply in real time, as if it were just next door. The implications are staggering, not just for exploration, but for our very conception of time and space. Experiments like quantum teleportation have already shown us glimpses of this future. In labs around the world, scientists have successfully transferred the quantum state of one particle to another across distances. While these experiments are still in their infancy, they hint at a future where quantum networks could become the backbone of cosmic communication. Think of it as cosmic whispers, tiny, nearly imperceptible signals carrying profound truths across the void. These whispers could one day connect civilizations separated by light years, creating a web of communication that transcends the limits of light speed. This quest isn't just about technology, it's about the role of quantum mechanics in shaping our understanding of the cosmos. Quantum entanglement challenges our classical notions of distance and separation, offering a glimpse into a universe where everything is interconnected in ways we're only beginning to comprehend. As we explore the potential of quantum communication, we're not just building tools, we're uncovering the fundamental fabric of reality itself. And in doing so, we're taking another step toward unraveling the mysteries of cosmic evolution. Picture the universe in its earliest moments, a seething, chaotic sea of energy where the rules of classical physics break down and quantum mechanics takes the reins. In this primordial chaos, tiny quantum fluctuations, no larger than a billionth of a meter, rippled through the fabric of space and time. These seemingly insignificant ripples were the seeds of everything we see today. Over billions of years, gravity amplified these fluctuations, pulling matter together to form galaxies, stars, and planets. It's almost poetic, the microscopic world of quantum mechanics shaping the vast cosmic structures that define our universe. But quantum mechanics didn't just set the stage for the universe's grand architecture. It also played a starring role in the creation of the elements themselves. Inside the cores of stars, quantum tunneling allows particles to overcome insurmountable barriers, enabling the fusion of hydrogen into helium and heavier elements. This process, known as stellar nucleosynthesis, is the cosmic forge that transforms the simplest atoms into the building blocks of life. Without quantum mechanics, the carbon in your cells, the oxygen in your breath, and the iron in your blood would never exist. It's a quantum dance, choreographed over billions of years, that has made the universe not only habitable but teeming with complexity. Now, as we peer out into the cosmos, we're beginning to see how these quantum fingerprints might extend beyond our own galaxy. The search for exoplanets, worlds orbiting distant stars, has revealed a staggering diversity of planetary systems. But what if these planets also bear the marks of quantum processes? Could quantum mechanics hold the key to understanding their formation, their atmospheres, or even the potential for life? This quest isn't just about looking back in time. It's about uncovering the quantum signatures that might shape the future of cosmic exploration. As we venture into the 16th of our quantum quests, let's turn our gaze to the skies, not just to the stars, but to the worlds orbiting them. Exoplanets, those distant planets beyond our solar system, hold secrets that could redefine our understanding of life in the universe. But how do we uncover those secrets from light years away? The answer lies in the subtle dance of quantum mechanics and the fingerprints it leaves behind in the atmospheres of these far-off worlds. Quantum spectroscopy is our cosmic magnifying glass. By analyzing the light that passes through an exoplanet's atmosphere, we can decode its chemical composition in astonishing detail. It's like reading the fine print of a cosmic contract. Every molecule absorbs light in a unique way, leaving behind a signature that quantum mechanics helps us interpret. Oxygen, methane, even water vapor, these aren't just chemicals, they're potential biosignatures, clues that life might exist beyond Earth. Imagine these signatures as cosmic fingerprints. Just as no two people share the exact same fingerprint, no two planets have identical atmospheric compositions. Quantum spectroscopy allows us to detect these unique patterns, even from unfathomable distances. For instance, the presence of oxygen and methane together could hint at biological processes, as these gases are often produced by living organisms. It's like finding a message in a bottle, except the bottle is a planet and the message is written in light. But quantum mechanics doesn't just stop at detection. It also offers insights into the anomalies we observe. Why does a particular wavelength of light behave differently than expected? What hidden forces are at play in these atmospheric signatures? By applying quantum principles, we can unravel these mysteries, piecing together the story of not just one exoplanet, but potentially thousands. This quest isn't just about finding life, it's about understanding the universe's intricate design, one quantum signature at a time. As we explore these cosmic fingerprints, we're not just searching for answers, we're redefining what it means to explore. Quantum mechanics bridges the gap between the familiar and the unknown, turning distant starlight into a treasure trove of information. And with every discovery, we come closer to answering one of humanity's most profound questions. Are we alone in the cosmos? The cosmos is full of mysteries, but some of its most baffling phenomena might hold the key to understanding the quantum fabric of reality. Take fast radio bursts and gamma-ray bursts, for example. These fleeting, high-energy events light up the universe like cosmic fireworks, yet their origins remain shrouded in mystery. What if the answers lie not in the vastness of space, but in the tiny, intricate world of quantum mechanics? Some scientists speculate that these bursts could stem from quantum processes operating on cosmic scales. Imagine a quantum black hole, a hypothetical object so small yet so dense that it defies our classical understanding of physics. These mini black holes might evaporate in a burst of energy, releasing gamma rays or radio waves that travel across the universe. Or perhaps exotic particles, ones we've yet to discover, are colliding or decaying in ways that produce these spectacular emissions. These theories push the boundaries of what we know, blending the strange rules of quantum mechanics with the grand scale of astrophysics. It's as if the universe itself is performing experiments, testing the limits of our understanding, and while we're still piecing together the clues, the implications are staggering. If quantum anomalies like these can warp space and energy so profoundly, could they also hold the secret to manipulating time itself? This quest isn't just about unraveling the origins of cosmic fireworks. It's about exploring the deep connection between quantum mechanics and the very fabric of spacetime. As we dig deeper into these anomalies, we might find ourselves one step closer to unlocking the mysteries of quantum time travel, where the past, present, and future could intertwine in ways we've only dreamed of. What if time travel wasn't just the stuff of science fiction, but a real possibility hidden within the strange rules of quantum mechanics? This brings us to our 18th quest, a journey into the speculative yet fascinating idea that time travel might someday be within our reach. At the heart of this concept lies the mind-bending notion of closed, time-like curves, loops in spacetime that could, in theory, allow an object or even a person to travel back to a previous moment in time. These curves emerge from solutions to Einstein's equations of general relativity, suggesting that spacetime itself could be twisted into shapes that defy our everyday understanding of cause and effect. Now, imagine a cosmic shortcut, a tunnel connecting two distant points in spacetime. This is the essence of a wormhole, another key player in the time travel puzzle. Wormholes, also known as Einstein-Rosen bridges, are hypothetical structures that could link different regions of the universe, or even different universes altogether. But here's where quantum mechanics steps in. Quantum entanglement, that mysterious phenomenon where particles become interconnected across vast distances, might hold the key to stabilizing these wormholes. Some theories suggest that entangled particles could act as a kind of quantum glue, keeping the wormhole open long enough for something or someone to pass through. Of course, this is all still highly speculative. The laws of physics as we know them today don't provide a clear roadmap for building a time machine or creating a stable wormhole. But that's part of what makes this quest so thrilling. It pushes the boundaries of our understanding, forcing us to ask questions that challenge the very fabric of reality. What would it mean to manipulate time? Could we ever use these cosmic shortcuts to explore the past or the future? And if we could, should we? This leads us to the ethical implications of quantum discoveries, a topic we'll explore further in our next quest. For now, though, let's marvel at the idea that the universe might hold secrets even more extraordinary than we've dared to imagine. Quantum discoveries are nothing short of revolutionary, but with great power comes great responsibility. Let's take a moment to consider the ethical implications of these groundbreaking advancements. Imagine quantum computing, a tool so powerful it could solve problems in seconds that would take traditional computers millennia. But here's the catch. That same power could also crack the encryption systems that protect our most sensitive data, from financial transactions to national security. It's like handing someone a master key to every locked door in the world. The potential is awe-inspiring, but the risks are equally daunting. Then there's the mind-bending idea of the multiverse. If every possible outcome of every decision spawns a new universe, what does that mean for our sense of responsibility? If every choice creates a new reality, does it diminish the weight of our actions here and now? It's a philosophical quandary that challenges our understanding of morality and consequence. Some might argue that multiverse theories could lead to a dangerous sense of detachment, as if our choices no longer matter. Others see it as an opportunity to embrace the infinite possibilities of existence. Either way, it's a conversation we can't afford to ignore. These advancements are a bit like a cosmic double-edged sword. On one side, they promise to unlock the deepest secrets of the universe. On the other, they force us to confront profound ethical dilemmas. How do we ensure that quantum technologies are used for the greater good? Who gets to decide what's ethical in a field that's still so poorly understood? These are questions that demand collaboration between scientists, ethicists, policymakers, and the public. The stakes are too high to leave them unanswered. As we stand on the brink of a new era in quantum exploration, one thing is clear: the pursuit of knowledge must go hand in hand with a commitment to responsibility. The future of quantum science isn't just about what we can discover, it's about how we choose to wield that knowledge, and that's a quest that belongs to all of us. As we stand on the precipice of discovery, the 20th quest invites us to peer into the future of quantum exploration, a frontier where science fiction edges closer to science fact. Imagine a reality where quantum telescopes, far more powerful than anything we've built so far, allow us to observe the universe in ways that defy our current understanding. These aren't just tools for seeing farther, they're gateways to uncovering the hidden fabric of reality itself. By harnessing the strange properties of quantum entanglement, such telescopes could detect the faintest whispers of light from the edges of the cosmos, revealing secrets that have remained hidden for billions of years. But the quantum revolution doesn't stop there. Imagine space-based quantum labs orbiting high above Earth's atmosphere, free from the distortions and noise that hinder experiments on the ground. In these pristine environments, scientists could test the limits of quantum mechanics with unprecedented precision. What if these labs could simulate the conditions of the early universe, or recreate the extreme environments near black holes? The data gathered from these experiments could reshape our understanding of gravity, dark matter, and even the origins of space and time. This cosmic quantum frontier isn't just about technology, it's about redefining what's possible. It's a future where quantum computers might one day solve the equations of the universe, revealing the underlying laws that govern everything from the smallest particles to the largest galaxies. It's a future where the mysteries of dark energy and the multiverse might finally come into focus, thanks to the marriage of quantum mechanics and cosmology. And as we push these boundaries, we're not just exploring the universe, we're exploring the very nature of existence. Looking back on the 20 quantum quests we've embarked upon, it's clear that each one has been a stepping stone toward this grand vision. From the strange behavior of particles to the mind-bending implications of entanglement, these quests have illuminated the path forward. They've shown us that the universe is far stranger, far more interconnected, and far more wondrous than we ever imagined. And as we stand here, on the edge of this new frontier, one thing is certain: the journey is far from over. The next chapter of quantum exploration promises to be the most thrilling yet, as we continue our relentless pursuit of cosmic truths. As we reach the end of our journey through the 20 quantum quests for cosmic truths, it's impossible not to marvel at how deeply interconnected these ideas are. Each quest, from the strange behavior of particles to the mind-bending nature of black holes, reveals a piece of a grand cosmic puzzle. Together, they challenge everything we think we know about reality, inviting us to question the very fabric of existence. These aren't just isolated mysteries, they're threads woven into the same tapestry, pulling us closer to understanding the universe's deepest secrets. What makes these quests so extraordinary is their ability to inspire awe and curiosity in equal measure. They remind us that the cosmos is far stranger and more beautiful than we could ever imagine. Whether it's the dual nature of light, the bizarre implications of quantum entanglement, or the paradoxes of time itself, these ideas push the boundaries of human knowledge and imagination. They don't just challenge scientists, they invite all of us to look at the universe with fresh eyes and wonder. And that's the real magic of these quests. They're not just for physicists or astronomers, they're for anyone who's ever gazed at the stars and felt a spark of curiosity. They remind us that the universe is full of mysteries waiting to be explored, questions waiting to be answered, and stories waiting to be told. So, as we wrap up this cosmic journey, I encourage you to keep exploring, dive into these ideas, discuss them, and share your thoughts in the comments below. What part of the quantum cosmos fascinates you the most? Before we go, let's reflect on the words of physicist Richard Feynman, who once said, "The universe is not only stranger than we imagine, it is stranger than we can imagine." That's the beauty of these quests. They remind us that no matter how much we learn, the universe will always have more to teach us. If you've enjoyed this journey through the quantum cosmos, don't forget to subscribe and join us as we continue to unravel the mysteries of the universe together. Until next time, keep looking up and keep wondering.